Writing chemical equations. So here we have an example of an equation on the screen. This is the combustion of octane. So before the arrow, we have our reactants, and after the arrow, we have our products. We also have these state symbols. So these state symbols are used to indicate the state of matter. So we have liquid, gas, solid, and aqueous. Aqueous means that something has been dissolved in water and formed a solution. So if you think of something like table salt, that would be NaCl solid. If you think about something like water, that would be liquid. But if you're thinking about sodium chloride that's been dissolved in water, that would be aqueous. Another important thing to note is that energy can be a reactant or a product, and energy comes in lots of different forms. In this case, we're looking at energy as heat. But the combustion of octane would also produce light as well. So these are just different forms of energy. And they can be either a reactant or a product. So the reaction might absorb energy to occur or release energy as it occurs. Another thing to remember are our diatomic elements. So hydrogen, nitrogen, fluorine, oxygen, iodine, chlorine, and bromine. Whenever these are by themselves, they're going to be diatomic. So that's really important because if you say we're doing a reaction with oxygen, like we saw in the previous example, if you don't know that that's O2, you're going to have a hard time balancing the equation properly. Some other things that are going to be useful to know are these solubility rules. So we use this solubility guidelines to determine if a compound would be aqueous or if it would form a solid, a precipitate in solution. So for the first one, we have sodium nitrate. So I can look in two places. I can find sodium, which is considered a group 1 ion. Those are going to be the ones that are in the first column on the periodic table. I could also look at nitrate because I have sodium nitrate. And for both of these, they are soluble and there are no exceptions. So when something is soluble, that means that it's going to be aqueous. So soluble will mean aqueous and insoluble means solid. So next we have silver chloride. So I should look down here with the halides where chloride is. Halides are column 17 on your periodic table. So chlorides and halides are usually soluble. They're usually aqueous, except when combined with silver, lead, and mercury. So since this is silver chloride, it's going to be a solid. Next, we have barium sulfate. So the sulfates are all the way down at the bottom here. Sulfates are usually soluble, except when combined with barium. So barium sulfate is going to be solid as well. So we can look at the next one, which is ammonium carbonate. So there's two places I can look here. First, I can look at ammonium. That is always soluble with no exceptions. Or I could look at carbonate. Carbonate is always insoluble except when combined with ammonium. So the rules won't contradict themselves, and they're used to determine if something is going to be a solid or if it will be aqueous if it forms in solution. So we have magnesium burns in the presence of oxygen to form magnesium oxide. So magnesium is Mg, and we have this reacting with oxygen. That's one of those diatomic elements, and so we get O2. We want to form magnesium oxide. So magnesium is Mg, and in a compound, it would form a +2 charge based on its position in the second column on the periodic table. Oxide is going to form a -2 charge. So oxygen has those 6 valence electrons. It will gain 2 more, so we get a -2 charge. So plus 2 and minus 2 add up to 0, which works. And then we need to balance this equation. So I've got 2 oxygens, and on the other side only 1. So I'm going to put a 2 in front of MgO. So now my oxygen is balanced, 2 and 2. And then I'm going to need to put a 2 in front of magnesium to balance that. Last thing that we need to add here are states of matter. So magnesium is going to be a metal. It's a solid. Oxygen is a gas. And my product, when we do this reaction, is a powdery substance. So that would be solid. An electric current is run along a wire submerged in water. We make oxygen gas and hydrogen gas. So we're starting with H2O. Now, if you have H2O, like sitting in a glass, you wouldn't expect that that water would suddenly turn into hydrogen and oxygen. And that's because energy needs to be put in as a reactant here. So the electric current along the wire is supplying energy that allows this reaction to occur. So my products are going to be oxygen gas and hydrogen gas, both of those diatomic. We can go ahead and balance this equation. So hydrogen is good, 2 and 2, but I've got 1 oxygen and 2 oxygen. So I'm going to put a 2 in front of H2O, and that takes care of oxygen. But now I have 4 hydrogens, so I need to come throw a 2 in front of this other hydrogen here to balance my equation. The water, H2O, is a liquid, and we form hydrogen gas and oxygen gas. Hydrochloric acid reacts with magnesium metal. So hydrochloric acid, we have a hydroblankic acid. So that corresponds to an ending of "ide," meaning that this was originally chloride. Chloride has a -1 charge. It's an acid, so we need to put an H in front, which would form a +1 charge. So this works charge-wise. We have +1 and -1, and it adds up to 0. This is going to react with magnesium, and we're going to form magnesium chloride and hydrogen gas. So magnesium chloride is a metal and a nonmetal. It's ionic, so I'm going to have to worry about charges here. So magnesium is +2 and chlorine is -1, so I need 2 of those chlorides, and then we're going to have hydrogen gas. Now we can go ahead and balance. So we've got 2 hydrogen and 2 chlorine on the product side, so I need to put a 2 in front of HCl here. Hydrochloric acid is going to be in a solution form, so that's going to be aqueous. Magnesium metal, solid. And we're forming this magnesium chloride and hydrogen. So magnesium chloride, if we use our solubility rules, chlorides are always soluble. There's a couple of exceptions, but magnesium isn't one of them. So this would be aqueous, and we're also forming hydrogen gas. Now, when we do this reaction, we see that the beaker gets very warm. And that's because the reaction going on inside the beaker is giving off heat. So the beaker and the surroundings warm up. Hydrogen gas, that's going to be H2. That reacts explosively with oxygen gas, and we're going to form water vapor. So to balance this, we need to stick a 2 in front of H2O. That balances oxygen. And then I need to put a 2 in front of H2. So this is the opposite of the equation we saw previously, where water broke down into hydrogen and oxygen. So hydrogen gas and oxygen gas and water vapor is going to be gas. We also know that when this happens, it's an explosion. And an explosion means it's giving off energy in the form of light, heat, and sound. So energy is going to be a product here. Copper 2 sulfate solution reacts with sodium hydroxide solution. So we have Cu +2 here, and sulfate is going to be -2. And it says that this is aqueous. This is going to react with sodium hydroxide. So these are all ionic compounds, so we have to make sure their charges add up to 0. Plus and minus 1 does, and it says this is a solution. We are going to form copper 2 hydroxide. So I need 2 hydroxides here. And we're going to form sodium sulfate. Since SO4 has a -2 charge, I need 2 sodiums here. Okay, so we can check if this equation is balanced. We've got 2 sodium and 2 hydroxide over here, so I'm going to need to put a 2 in front of this guy. Now, these two products, we need to figure out what their state of matter is. So if we look at copper hydroxide, hydroxides are usually soluble except for a couple of exceptions, and copper hydroxide is one of them. So copper hydroxide is going to be our solid. Sodium sulfate, sodium compounds are always soluble, no exceptions. So that guy's going to be aqueous.